Okay. Now, to do calculus, we need to be able to measure how close are 2 points, and so that we can define the limits and the convergence. Therefore, we need additional structure on Rn. This is provided by scalar product. So we defined scalar product, also called inner product, of 2 elements x and y. What's the scalar product of x and y? Okay, so the notation is xy. Sometimes we also use the dot notation, x dot y. And of course, this product sometimes is called dot product. It's also some people use this terminology. So what's this? This is defined to be the sum of the multiplication of the corresponding components of x and y. So this is the definition of scalar product. So Rn, which this scalar product, is called Euclidean space. Okay. Now we will discuss the basic property of this scalar product. This is a proposition. We have these properties. Firstly, this is non-negative, and for any x, the scalar product of x to itself is non-negative, and if this is 0, this can only happen if x is 0, if and only if x is 0. The second property is that symmetry, xy equals yx. Of course, if you prefer the dot notation, this is the same as x dot y equal y dot x. Okay, just a different notation, but the meaning is the same. The third one is that for lambda and mu real numbers and the xy elements in Rn, then lambda x plus mu y is an element in Rn. Therefore, we can take a scalar product of this sum, which the third element in Rn, z. What's this? This will be equal to lambda and the scalar product of x and z plus mu times y and z. This means the scalar product is linear over the first component. By the second property, symmetry, we also know that the scalar product is also linear over the third variable. That is to say, x lambda y plus mu z will also equal to lambda xy plus mu xz. Okay. Now we notice this. Any element, the scalar product to itself is non-negative, so that we can define the norm of an element. For x in Rn, the norm of x is defined to be the square root of the scalar product of x to itself. If x is written in its coordinates x1, xn, then this is exactly xi square, the sum of xi square then take the square root. Sometimes we denote the norm by a simpler notation, that is the norm of x can also be denoted by this simpler notation, which is single bar, like absolute value. So this notation is much simpler, and we prefer to use this simpler one. And also we consider the case n equal to 1. If n is 1, by identifying x which x R1 is exactly the real number R, and the norm of x, that is this is the norm we just introduced for the case n equal to 1. It's exactly the absolute value. So this justified this notation for norm using the single bar notation. Okay. So before we discuss the basic property of the norm, we need to prove this Cauchy-Schwarz inequality, which says that for any x and y in Rn, the absolute value of their scalar product is not greater than the multiplication of their norm. So this inequality is called Cauchy-Schwarz inequality. For the proof, it's quite easy. For any real number t, by the property of scalar product, we have x plus ty and x plus ty is non-negative. We expanded the right hand side. This will be xx plus, here using the linearity over the second variable, we have x and ty, the scalar product of x and ty. This which is t xy. Similarly, this term ty and x will give us tyx. Finally, the two ty give us t square yy. So this is the square of the norm of x plus this two term give us 2t xy, then t square y norm square. Because this is non-negative for all t, the right hand side is a quadratic polynomial, which is never negative. So we see that the coefficient of this quadratic polynomial will satisfy the square of this minus will be no positive. Hence, our Cauchy-Schwarz inequality follows. Okay, so we have proved the Cauchy-Schwarz inequality. Using the Cauchy-Schwarz inequality, we can discuss some basic property of the norm. Proposition. Firstly, for any x in Rn, the norm is non-negative, and the norm is 0 if and only if x is the 0 element in Rn. Secondly, for lambda a real number, and of course x is in Rn, we have the norm of lambda x is equal to the absolute value of lambda and the norm of x. So this equality is a little confusing because the bars has different meaning. For this term, for lambda, this is the absolute value of the real number lambda. The other two pairs of bars means the norm in Rn, because lambda x and the x are all elements in Rn. Therefore, the bar surrounding them means the norm. If you are not acquainted with this notation, maybe you would like to write this result by this way. We use the double bar to denote norm, so this will be not confusing. This will be more clear. But the notation is more complicated. If you are familiar with our study, you will prefer to use this more simple notation. Okay, so this is the second property of the norm.